Welcome to a lesson on projection, which is an application of the dot product of vectors. Topic 2 here, the second part. So there's actually an application of the projection, which is an application of the dot product. But we're just going to focus on a little bit of the physics for now and mostly stick to the pure math. So in front of us here we have a box. And in everyday life, there are many times that we need to push a box, or pull a box, or lift a box, or drop a box. Move a box from point A to point B. And in this particular case, I sketched a vector v, which is blue, and a vector u in a certain direction that we're kind of pulling the box. So for this example, we could just pretend that the u vector is maybe like a string that's attached to the box that we're pulling in that direction. So you could think of it as like maybe a radio flyer wagon that you're pulling with the handle in that certain direction. So if this was a wagon and our arm was kind of at this angle and we're standing up, we're basically pulling the wagon towards us, but there's an effective amount of pulling that's happening just on the horizontal aspect. So basically what's happening is you're wasting some energy pulling in this direction, and only some of the force is being applied in the direction that you actually want, which is along the ground. So if we wanted to find out what the actual effective force was, we could kind of think about this as a situation where the sun is shining down on the u vector. And that may seem a little bit weird to you at first, but let me just remind you that when we actually project something on a screen, there's a certain amount of angle that is happening. So if you have a little projector with a lens, it's projecting out onto a vertical screen, and you basically have a viewing angle, and there is light involved, and that light is really helping that image be projected on the wall. Alright, so in this case, the way that I'll highlight this or illuminate this, if you will, is let's pretend that the sun is shining down on our situation, and the sun is very happy about you moving the box. And when we do that, the sun actually is creating a shadow of the green vector onto the blue vector, and it creates a 90-degree angle. So it's kind of like dropping in altitude. And by doing that, what we actually calculate, or we could think that we calculated just graphically, is the projection of u onto v, which ends kind of where my arrow is right here. So to highlight that even further, so call that v, what ends up happening to u is it's being projected onto v, so this green part onto v, and I'm just trying to sketch it especially thick here, and it looks as if the green vector gets shorter. And the reason why that would be the case is, well, you know why, that if you pull a wagon or a box in a certain direction that's vertical, has some sort of vertical aspect to it, then you're only pulling it so much in a horizontal direction. So you're wasting a little bit of the energy. So that new green vector is called the projection of u onto v. And that's the only thing we're going to focus on in this video. Now this other little vector down here, this could be called something else. I could call it u1 if I wanted to. Alright, and I'll show you how to do some of that. So, just to summarize what we just did, if u is a force, then the projection of u onto v represents the effective force in the direction of v. The projection of u onto v represents the effective force in the direction of v. But why? Why would we do this? Why would we even consider this just a pleasant act of mathematics and physics together? No, really we're just doing this to determine the amount of force. If we knew the amount of force actually, and we applied that force in a certain amount of time or a certain amount of distance, then that helps us actually calculate work, which is very, very much a physics topic. But what's neat, since this is a concept in pre-calculus, it leads up to some calculus concepts too. So physics and pre-calc kind of meet in a few different ways, and so does calculus and physics. Now, What we're actually asking still is how much of u is going in the direction of v. So let me go back there. How much of this u is actually going in the direction of v? So what percentage of that vector, what fraction of that vector is going in the direction of the blue vector? Well, there's a formula for this. And the formula starts with this. It starts with the notation of projection of u onto v. Notice the u is over the v. And that's equal to the magnitude of u. Oh, shoot, hold on. I need to share with you a little bit more before we do this. First of all, I want to define this u. What is the u vector? The vector u can be described in two components. The magnitude of u times cosine theta, comma, the magnitude of u times sine theta. Now this shouldn't seem foreign to you at this point in this course, because all we're really doing right here is saying we have some sort of magnitude, some sort of length of the vector, and we're going in the x component, the cosine theta, so the adjacent side. And then same idea, but for the opposite side. So going back to the picture, that magnitude of u is just that how long that hypotenuse is, and then cosine theta gives you the horizontal aspect, and sine gives you the vertical aspect. Okay, now that that's said, let's go back to that projection of u onto v formula. And so what that looks like is the magnitude of u times cosine theta. I'll explain exactly how we got that in just a moment. Times v over the magnitude of v. All right, this first piece, magnitude of u times cosine theta, this is how much of u. How much of u. Think about it. How much of u, that horizontal aspect with the magnitude. How much of it? Because that's all we care about is that horizontal piece. And then this next piece is just giving us the direction. The direction of v. Remember that that's actually the unit vector, v over magnitude of v. So it's just giving us a direction. And then the first piece is how much of u. We just want that portion. All right, now this is all equal to something that we could use before. So that cosine theta, recall that that could be defined in terms of the angle in between two vectors. So the magnitude of u stays as the coefficient basically, and cosine theta becomes u dot v, this comes from our formula before, over the magnitude of u times the magnitude of v. And that's a formula you want to memorize because then it helps you with this piece. And all of that times that directional piece. All right, so we're about to create the final formula here, and it's coming up here. So one more step, and then I'll create a final step. So that becomes u dot v, so the dot product. And notice that up above, some of the magnitudes cancel. And then in the denominator, we get the magnitude of v squared. And then what we'll have is the actual component form of v. So basically this is our formula. I'm going to rewrite it one more way, but this is u dot v over the magnitude of v squared times the actual vector. Alright, so it's the answer to this question or example is going to be a vector. And so that means the projection of u onto v is u dot v over magnitude of v squared. Oh, sorry, that's what we already had. Okay, great. That's the same thing. In my notes I had something over here. I wrote the magnitude of v twice. So that is our formula that we're going to stick with. Okay, now let me show you how this actually comes to light. So here's the one example we'll do. Let's take us a few minutes, calculate the projection of u onto v if we're given these two vectors, u equals 6 comma 2 and 5 negative 5. So let's stick with the fact that u is still green, so that's 6 comma 2. So I'll create my vector right over here. And I will create a little arrow on the end of it. And then v is 5 comma negative 5. So there's my point, 5 negative 5. And we basically have a vector going in the, and we have a 45-degree angle that's kind of in between the x-axis and v. So that's v, and that's u. So first I want to make a few definitions. The first one being that u is actually a component or a sum of two other vectors, which is u1 plus u2. And then also these two. So these three things I'll just set in motion for now, and I'll try to explain as we go, but basically u is u1 plus u2, so basically we'll get the component, the actual vector u that will be projected onto v, that'll be what we'll call u1, and then there's another vector that will connect those two together. So the first thing that we want to do is calculate u dot v, because that's part of our formula. So that's 6 times 5, which is 30, minus 2 times 5, which is 10. 2 times negative 5, which is negative 10. So that's 20. And then we need to calculate the magnitude of v, so I could kind of do that in my head as well a little bit. So that's 25 and negative 5 squared, which is 25. So that's the square root of 50. Now I'm going to leave that alone because notice in the previous page we have the fact that we're squaring the magnitude of v. So I'm just going to leave it in square root form. Then I will just get the formula going. So the projection of u onto v, which is u1, is the dot product, that 20, divided by the magnitude of v squared, which is 50, root 50 squared, times the actual vector v, which is 5, negative 5. So notice how you'll get a vector at the end. So I'm going to pause here and I just want to point out the fact that the projection of u onto v is a fractional portion of the vector v. The same thing happened here in this first picture. The green vector is just a portion of v. Okay? So that ultimately ends with basically 2/5 of 5, 2/5 of 5, which is 2, and 2/5 of negative 5, which is negative 2. So now I'll take that 2, negative 2 and sketch it on the graph. So 2, negative 2 shows up right there. And I've projected u onto v. Now, this is slightly different than the very first visual I gave you. We're kind of pretending that the sun is like this because the v vector is not just horizontal, it's diagonal as well. So then that sun shines and creates this triangle, like so. So the next thing that I'll do is I'm going to redefine u2 as this yellow vector so that I can calculate it here. u2 is equal to, well, I could just look at it now. I could go look at the graph and I could say it starts here and goes 1, 2, 3, 4 units to the right and 4 units up. But how do I get that 4, 4 from my information? Well, I take that 6 comma 2, which is u, and I subtract, just like I said right here, u minus u1, I subtract 2, negative 2. And that gives me, oh my gosh, 6 minus 2 is 4. 2 minus negative 2 is 4. Hey, that's what the picture says. So if we don't have a picture that's easy to sketch, now we know we can set this up this way and apply the pattern. Alright, and then finally, u is equal to u1 plus u2. So the only reason I did that is so that I could actually prove that those two things together would give me the original vector I started with. So u1 is 2, negative 2, and u2 is 4 comma 4. So I'll just add these two together. Those two together, 2 plus 4 is 6, and negative 2 plus 4 is 2. Hey, that's what I started with. Awesome. So that just proves that if I add the two vectors together, u1 in green and u2 in yellow, then we get the exact vector that I started with, and our calculations were correct. Okay, that video took a little bit longer, but I want to make sure I get every detail for you so that if you come across some problems that have some fractions in there, you have a nice model to use as that. So if you do come across those fractions, just stick with it and everything will work out at the end. Thanks a bunch.